So in the final week of this course, we will be exploring the notion of diagonalizability a bit further. So if you recall from the material in the 8th week of this course, we had defined a linear operator on a vector space to be, on a finite dimensional vector space to be diagonalizable if we can get hold of a basis consisting of eigenvectors of T. In the setting of an inner product space, we can say a little more about diagonalizability of certain special type of operators. So in this week, we will explore some of these special type of operators and also study the property of diagonalizability of these operators. So let's begin by defining what is a normal operator on a finite dimensional inner product space. So let's begin by considering the case when linear operator T, when it is given on an inner product space, a finite dimensional inner product space, suppose we have an orthonormal basis consisting of eigenvectors of T. Let's consider that particular scenario. So the setup is this. Let V be a finite dimensional inner product space and we have a linear operator and T. Let me start using this notation L of V, which is basically the space of all linear operators on V, linear transformations from V to itself, and L of V T be in L of V. Consider, suppose we get hold of an orthonormal basis beta, an orthonormal basis of beta basis of V consisting of eigenvectors of T. This is amongst the best possible setup we can think of, eigenvectors of T. So not only is T diagonalizable, but we can also get hold of bases which consists of eigenvectors which are orthogonal to each, orthonormal rather than orthogonal. Then let's see what happens. Then let's consider the matrix of T. This is a diagonal matrix. That's something which we know for sure. It is already a diagonal matrix without it being an orthonormal basis. In particular, here it is an orthonormal basis as well. But the moment we are in an inner product, in a finite dimensional inner product space, and we have an orthonormal basis, and if we look at the matrix of T with respect to this particular orthonormal basis, we also know what is the matrix of T with respect to the matrix of T star with respect to the orthonormal basis. Then by whatever we have done in the previous week, the matrix of T star with respect to the basis beta, this is nothing but the adjoint of the matrix of T with respect to beta. This is equal to the matrix of T with respect to beta adjoint. Recall that the adjoint of a matrix is the conjugate transpose. But we know that T beta beta here in this case is a diagonal matrix. So what can we say about the conjugate transpose of the diagonal matrix? We again know that this is a diagonal matrix. Since T beta beta is diagonal, so is the adjoint of that. And we know that diagonal matrices commute when we multiply. So since diagonal matrices commute, well, A and B are said to commute if AB is equal to BA, commutativity, that commute. So if the T beta beta is a diagonal matrix, so is T beta beta adjoint, and hence T beta beta times T beta beta adjoint is equal to the adjoint of the matrix T beta beta times the matrix of T beta beta. Now we will invoke whatever we have just observed from the previous week. We know that the adjoint of the matrix of T with respect to beta is the matrix of the adjoint. So, let us use that and conclude here that this is okay. Let me just write one more step. This is just telling us that T beta beta times T star beta beta is equal to T star beta beta, the adjoint of T, times the matrix of T itself. But this also implies that the matrix of T T star with respect to beta is equal to the matrix of T star T with respect to beta. So, what it tells us is that if with respect to this orthonormal basis, the matrix of T is diagonal, then T and T star commute. And now, as it turns out, this is the right notion to look at to study the diagonalizability of operators, to study T's. So, there is a version of the diagonalizability of operators which satisfy this particular condition, namely T T star is equal to, so this also further this also implies that T T star is equal to star T, right. So, this is exactly what is called as a normal operator. So, let me now give you a definition. So, we just saw that if the linear transformation, linear operator on V has a basis, orthonormal basis consisting of, rather if V has an orthonormal basis consisting of eigenvectors of a linear operator T, then the matrix of T is going to commute with the matrix of T star, and from that we concluded that T T star is equal to T star times T. So, that is what is called as normality, normal operator. So, let V be a finite dimensional inner product space. And the setup was just as we defined, and T be a linear operator on V. So, it is a finite dimensional inner product space and T is a linear operator on V. We say that T is normal. So, let me write the word and underline it to stress upon the fact that we are defining this. We say that T is normal, T is a normal operator. So, must be then both this. If T T star is equal to T star T. Notice that T is a linear operator. So, it is a linear transformation from V to itself, and therefore, the adjoint is also from V to itself. So, T T star makes sense, and we demand further that T T star is equal to T star T. Okay, let us look at a few examples. Let T be from say R2 to R2, and let us look at T of say x comma y to be equal to minus of maybe y comma minus of x. Let us look at the map of x comma y going to y comma minus of x. So, let me just quickly compute the matrix of T with respect to the orthonormal basis consisting of the standard vectors. That will be equal to, what will be T of 1 0, T of 1 0 will be 0 minus 1. So, this is going to be 0 minus 1, and how about 0 1, T of 0 1 will be 1 comma 0, and how about T beta adjoint, that is just going to be equal to 0 minus 1 1 0. And if you look at what is T star of x comma y is, that will just be multiplication by this matrix. All this is basically things which we are borrowing from the previous week's lectures. So, this is going to be x comma y is minus y comma x. So, if you notice, we started off with T of x comma y being equal to y comma minus x. We have ended up with T star of x comma y being equal to minus of y comma x. So, let us see what is T star of x comma y. T star of x comma y is just equal to t of minus of y comma x, which is equal to x comma y. And what is t star t of x comma y? T star t of x comma y is t star of y comma minus x. If I am not mistaken, that's what our definition of t of x y is. Yes. And this again by definition is going to be equal to x comma y, because t star of x comma y is minus of y comma x. So this implies that t star in this case is equal to t star t. Okay, so this is an example of a linear operator which is normal. A non-example that is also in order. So let's look at t of x y being equal to say 0 comma x instead of minus y comma x. Let's consider this, and let's see what is e beta with respect to the standard basis, the orthonormal basis consisting of the standard basis vectors. This will just turn out to be equal to t of 1 comma 0 is just 0 comma 1, and then there is this. How about e beta adjoint? This is just going to be equal to 0 1 0 0. And what does that mean? That means that t star of x comma y is equal to y comma 0. Well, let's see what is t star of x comma y. This is equal to t of y comma 0. T, remember, t of x comma y is 0 comma x. So this is just going to be equal to 0 comma y. Yeah, that is right. So let me be a little careful here. Y comma 0 is sent to 0 comma y. How about t star t of x comma y? This just will be t star of x comma y is 0 comma x, which is equal to now x comma 0. So observe that for say 1 comma 1, t star is not equal to t star t. Hence, E is not normal. In this case, we should actually also look at the fact that there are matrices involved. So there can be an analogous notion of normality that can be defined for matrices. So let me give that definition here as well. Let A be an n cross n matrix. We say that is a normal matrix A adjoint times A. So we say that A is a normal matrix if A adjoint is equal to A adjoint times A. So you can check, I will not go and check for you. This is this particular matrix which now I am boxing in green is just going to turn out to be a normal matrix. So needless to say, there is a strong relation between normal matrices and normal operators. We'll capture that in the next proposition. So proposition. So the setup is going to be the same. Let T be a linear operator on a finite dimensional inner product space. So let T be a linear operator on a finite dimensional inner product space. And suppose we have a orthonormal basis, some orthonormal basis. So let beta be an orthonormal basis of T. Then T is a normal linear operator if and only if T beta beta is a normal matrix. In the case of beta being an orthonormal basis consisting of eigenvectors of T, we had already checked that this is going to be a normal operator, but this is true in the general case as well. So let's give a proof of this and establish this. So what do we know about T? We know that T is a normal operator. Since T is normal, okay, let's the forward direction. Since T is normal, let me just put a arrow here as of now. Let T be a normal operator. We have that T star is equal to T star T. That's the very definition of T being normal. Now let's look at the matrix of T star with respect to beta. Well, that just will be equal to T star T with respect to beta. And we know that, so let me put implications here. And this implies in particular that the matrix of T beta beta will be equal to the matrix of times the T star matrix of T star with respect to beta will be the matrix of T star with respect to beta times the matrix of T with respect to beta. But beta is now an orthonormal basis. That's where the key feature of inner product spaces come into the picture. Because it is an orthonormal basis, we know what the definition, what will be the matrix of the adjoint. It is just going to be the adjoint of the matrix of T by one of the theorems we have proved in the previous week. So this is just going to be equal to T star T, maybe I should be a bit careful. This is T beta beta adjoint times the matrix of T with respect to beta. But that just tells us that T beta beta is a normal matrix. So yes, we have proved one direction. We have proved that if T is a normal linear operator, then T beta beta is a normal matrix. So now let's prove the converse. To prove the converse, I'll just run you through the steps and notice for you that if T is a normal matrix, this implies that this particular identity is satisfied, and if this is satisfied, this implies the because it's a orthonormal basis, the adjoint of the matrix of T is the matrix of the adjoint, and this implies that T star of beta beta is the same as T star T of with respect to beta beta, and that implies that T star is equal to T star T as linear operators, which implies that T is normal. So let me just change it a bit. So let me just say that T is normal will imply all this up till here and back. That way we have established this result. Normal operators have some nice properties. So let's discuss some of them. We'll first discuss the eigenvalues and eigenvectors of normal operators. In the last week, we have already seen that if lambda is an eigenvalue of T, then lambda bar is an eigenvalue of T star. But we had no clue about what the eigenvectors of lambda bar would be, of T star would be corresponding to lambda bar. As it turns out, there is a good chance that if V is an eigenvector corresponding to lambda of T, then we need not be an eigenvector of lambda bar corresponding to T star. However, in the case of normal operators, that is forced. So that is the content of our next theorem. So let me just write down the theorem for you. So again, let T be a linear operator on a finite dimensional inner product space. Then V is an eigenvector of T corresponding to the eigenvalue lambda if and only if V is an eigenvector of T star corresponding to lambda bar. So, we already know that lambda bar has to be an eigenvalue of T star, but this theorem tells us that the same eigenvector works for lambda bar as well. So, then if and only if V is an eigenvector of T star corresponding to lambda bar. The proof is actually quite straightforward. We are going to use the properties of a normal operator quite extensively. So, let us look at T star V minus lambda bar V norm of this. We will prove that this is equal to 0. So, rather we will prove that the square is 0, the length of the square of the length of T star V minus lambda bar V. But that is just equal to the inner product of T star V minus lambda bar V with itself, and this is equal to the inner product of T star V with T star V. Let us see, minus inner product of T star V comma lambda bar V minus inner product of lambda bar V with T star V, and finally this is going to be inner product of lambda V lambda bar V. This is the exact expression that we will have. But then by the properties of the adjoint, this is just the inner product of V with T star V. And how about the second term? The second term will be the inner product of V with T of lambda bar V, which is equal to, we will come to that. So, this minus similarly T of lambda bar V comma V plus mod lambda square times inner product of V with itself. Now, T is a normal operator. This implies that T star is equal to T star T. This is equal to hence V comma T star T V. How about here? T of lambda bar V is lambda bar times T of V, which is equal to V comma mod lambda square times V minus yet again minus mod lambda square times V comma V plus mod lambda square times V comma V. Now, let us look at it a little more carefully. The mod lambda square will come out here, that will cancel with the last term. Finally, what we will be left is V T star T V minus inner product of V mod lambda square V. So, the second term is just going to be equal to mod lambda square of inner product with V with itself. And how about the first term? The first term is just going to be T V with itself, inner product of T V with itself, because this is the definition of the adjoint. Recall that the adjoint of T is T itself. So, that is what we have used here, and we will now use the fact that this is lambda V and again lambda V, because V is an eigenvalue of T minus mod lambda square times inner product of V with itself. But this is equal to lambda times lambda bar, which is mod lambda square times the inner product of V with itself minus mod lambda square the inner product of V with itself, and which is equal to 0. So, what had we started off with? We had started off with the length of T star V minus lambda bar V, and we have just established that that object has to be necessarily equal to 0. Hence, length of T star V minus lambda bar V is equal to 0, which implies that T star V minus lambda bar V is equal to 0, the 0 vector, which is equal to, hence implies that T star V is equal to lambda bar V. So, that establishes the forward direction. So, we have assumed that V is an eigenvector corresponding to lambda of T, and we have established that lambda bar V is an eigenvector of lambda bar corresponding to lambda bar of the adjoint of T. The converse is also quite similar. I will not prove that. I will just leave it as an exercise because the proof is exactly the same. You could also use the fact that the adjoint of T is T, and then use whatever we have used, whatever we have just proved. You can apply it to T star and T star star. That is also another way of looking at it. Anyway, so the converse also follows. So I'll just leave that as an exercise. Converse is an exercise for you. Either way, it's a simple observation though. And with that, we have established that the eigenvector of T will also be an eigenvector of T star. In fact, the eigenvectors of normal operators behave in a very special manner. So, in the next proposition, we will capture exactly that. We will prove that if you have eigenvectors corresponding to distinct eigenvalues, we have already seen that they are linearly independent, right? We will now show that if T is a normal operator, then the distinct eigenvalue eigenvectors corresponding to distinct eigenvalues, they will also turn out to be orthogonal to each other. So we can, yeah, so let's see that that's not generally the case. Only in the case of normal operators can we say that. If you look at a normal operator, not a normal operator on a finite dimensional inner product space, we cannot conclude this. So proposition which captures what I just said, that, okay, so let me just put it up. I should slowly, maybe I should have just mentioned that in the entire lecture. T will be a linear operator on a finite dimensional vector space. Then T is, okay, suppose lambda 1 and lambda 2 are distinct eigenvalues of T. And V1 comma V2 be corresponding eigenvectors. V1 and V2 be corresponding eigenvectors. So they are eigenvectors corresponding to distinct eigenvalues. Then V1 is orthogonal to V2. So let's see, let's look at a proof of this particular proposition. So what do we know about, let's see, what is TV comma TV1 comma V2. We know that this is equal to, or maybe I should start like this, lambda 1 times V1 comma V2. If you look at this particular number, this is after all a scalar, right? So this is equal to the inner product of lambda 1 times V1 comma V2 by the very basic properties of the inner product. Now that is equal to, because V1 is an eigenvector corresponding to lambda 1, this is just TV1 inner product with V2. But now we will invoke the definition of an adjoint, or the property of an adjoint of T, to conclude that this is V1 inner product with T star of V2, the adjoint of V2, and V2 is an eigenvector of T corresponding to lambda 2. So V2 is also hence an eigenvector of T star corresponding to lambda 2 bar. That's the content of the previous proposition. So this is just V1 comma lambda 2 bar times V2, and by the properties of inner product, this is lambda 2 times the inner product of V1 with V2. What does that mean? This implies that lambda 1 minus lambda 2 times the inner product of V1 and V2, this is just equal to the scalar 0. But we observed that lambda 1 and lambda 2, the hypothesis tells us that lambda 1 is not equal to lambda 2. So, lambda 1 minus lambda 2 cannot be 0. So, the product of two numbers equal to 0 and one of them is non-zero forces the other to be equal to 0. So, V1 comma V2 in the field. So, the field of scalars. So, this is just going to be equal to 0, and that is precisely what we had set out to prove. So, V1 is orthogonal to V2. Right. So, normal operators have some really nice properties when it comes to eigenvectors as well. So, eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Well, this is going to play a very crucial role in proving that in the right setup, normal operators is diagonalizable. We will come to that later. Let us explore a few more properties of normal operators. So, I will capture the next in the following proposition. So, yet again let T, did I observe that T is normal in this? Oh yeah, T be a normal linear operator. This is true only in the case when uh, T is indeed a normal linear operator. Otherwise, we cannot conclude something of this sort. Yeah, I hope I have written the case here as well. Okay, yet again I missed the condition in the, so this lecture, all the linear operators that we are considering are normal. So this is okay. This statement was giving us a character, the previous statement was giving us a characterization of T being normal, and here we are studying the properties of normal operators. So these are all properties of normal operators. Right. So what next? So let T be a normal, let me not miss it this time, normal linear operator on a finite dimensional inner product space. Then the length of T star V is the same as the length of TV for all V. Then the length of T star V is equal to the length of TV for all V in capital V. This is quite straightforward actually. Let us give a quick proof. So, we will rather prove that the square is the same. These are the standard tricks that we use in inner product spaces, because the length square is just the inner product of T star V with itself. The inner product of T star V with itself. The adjoint of T is T. So, this is going to be equal to V T star V, and T is a normal operator. So, T star is equal to T star T, V comma T star T V. But again, this by the property of the adjoint is just TV comma TV, which is the length of TV square. So, we started off with the length of T star V square, we ended up with the length of TV square. This implies that length of T star V is equal to the length of TV. So, T and T star have the TV and T star V have the same length for all V in capital V. So, that is something which we can say about normal operators. Okay, let us solve some problems now. So, just like in the previous week, we will try to solve as many problems as possible during the lectures itself. There will be no separate problem session. The problems will be integrated into the lectures. So, let us solve the first one. First problem states the following. So, let E be a linear operator from C3 to itself. Be a linear operator. such that t of say 1 comma 1 comma 1 is equal to 2 comma 2 comma 2. This information is given to us. Then prove that if t of if z1 z2 z3 is in the null space, belongs to the null space of T, then z1 plus z2 plus z3 is equal to 0. This is what we have to prove. So if z1 z2 z3 is in the null space, the sum of its coordinates is 0. So yeah, so what is it that we are given? Oh, this is not yet again I'm missing, I'm sorry to be missing, I'm sorry that I'm missing it again and again. We are considering only normal linear operators in this particular lecture. So yeah, T here is a normal linear operator. So let me just restate the problem here. T is a normal linear operator such that T of 1 1 1 is 2 2 2, and suppose z1 z2 z3 is in the null space of T, then the sum of the coordinates is equal to 0. So let's look at a solution. Okay, so what do we know about T of 1 comma 1 comma 1? That is just 2 comma 2 comma 2, which is 2 times 1 comma 1 comma 1, which implies that 1 1 1 is an eigenvector corresponding to the eigenvalue 2. And what do we know about z1 z2 z3? z1 z2 z3 is in the null space. It's in the null space of T or the kernel of T. This implies that z1 plus, sorry, not z1 plus, T of z1 z2 z3, this is the 0 vector, but that is just equal to 0 times z1 z2 z3. So that means that, okay, further if the null space of linear operator is non-zero, if it is not an injective linear transformation, then 0 is in particular an eigen value of T, and any non-zero vector in the null space will turn out to be an eigenvector corresponding to 0. So here in this case, z1 z2 z3 is an eigenvalue, is an eigenvector of T corresponding to the eigenvalue 0. So maybe I should add in the problem here that be a non-zero vector. Actually, let me not bother about that, because if it is indeed the 0 vector, then there is nothing to prove, right? So let me not unnecessarily, it is there, it's self-evident. If z1 z2 z3 is 0, then z1 plus z2 plus z3 is also equal to 0. So in particular, this is true for all vectors in the null space of T. B is an eigenvector of T, right? That's what it means. If z1 z2 z3 is non-zero. If z1 z2 z3 is 0, I will not bother writing the argument down, because then z1 plus z2 plus z3 is anyway 0. Now, what does this mean corresponding to 0, to the eigenvalue 0? Yeah, maybe I should have finished this. Okay, what is the theorem which we have proved a bit earlier? We have proved that if this one, if you have a normal linear operator, if T is a normal linear operator on a finite dimensional vector space, and lambda 1 and lambda 2 are distinct eigenvalues of T, then its eigenvectors are going to be orthogonal to each other. So here in particular, what this tells us is that 0 and 2 are eigenvalues here, distinct eigenvalues. The inner product of z1, z2, z3 and 1 comma 1 comma 1, which are the eigenvectors corresponding to 0 and 2 respectively, this is going to be equal to 0. but by the inner product definition of the inner product, we know that Z1 plus Z2 plus Z3 is exactly the inner product of Z1, Z2, Z3 and 1 comma 1 comma 1, and hence we have concluded that this is equal to 0. We have solved the problem. Okay, another problem along the same lines. So let's consider in an abstract inner product space. So let T from V to itself be a normal operator on a finite dimensional inner product space. Suppose norm of V is equal to 2 equal to norm of W and T of V be equal to 3 V comma T of W be equal to 4W. Then calculate TV plus TW. Let's see. TV is equal to 3 times V and TW is equal to 4 times W. This indicates that V and W are orthogonal to each other because they are the eigenvectors corresponding to distinct eigenvalues. So let me first note that down. Solution. Since V and W are eigenvectors of T corresponding to distinct eigenvalues, again by that theorem, then inner product of V with W is 0. They are orthogonal to each other. So let's look at what is the length of TV plus TW. In fact, we will look at the square of the length of this. TV, if you notice, this is just equal to 3 times V, and the vector TW is 4 times W, the square of this. But we know that by Pythagoras theorem, if if V and W are orthogonal to each other, so will the vectors 3V and 4W be. They are after all scalars, right? So check that this implies 3V with 4W, which is just 12 times V comma W is equal to 0. And therefore, these are orthogonal vectors, and you are looking at the square of the length of the sum of two orthogonal vectors. By Pythagoras theorem, this is just equal to the length of 9 times V, 9 times the length of V square plus 16 times the length of W square. But length of V and length of W both are equal to 2, and therefore this is just 25 times 4, which is equal to 100. This implies that the length of TV plus TW, this is equal to 10. That's the number we are looking for. Yeah, maybe we should have proved this problem first. This is problem 3. Let's call it problem 3. So let T from V to itself be a linear operator, be the linear operator, or before that, let's fix two vectors. So let V0 comma W0 be in capital V. So we have seen this linear operator before, and define T from V to itself given by TV is equal to the inner product of V with V0 times W0. So here the question is to prove that, then prove that T is normal. Notice that in this case T is from V to itself. So T is normal. It's a special case of the linear operator we were considering last week. If and only if V0 and W0 are linearly dependent. Okay, let's look at that. Let's prove the forward direction first. Suppose T is normal. That means T star is equal to T star P. So we have calculated what T star is. Recall that T star of, let me just use W here for consistency, even though W is also some vector in V. This is going to be equal to W inner product with W naught times V naught, and T star W is just equal to the inner product of W with W naught times T W, right? Times T V naught. Why is this? Because T is a linear operator. But then this is equal to the inner product of, let me be a little careful, this is going to be W comma W naught times what is T V naught? T V naught by definition is V naught with itself, inner product of this, times W naught. So that is the definition of T, if you recall here. This is the scalar W time W comma W naught times the length of V naught square times W naught. Now let's look at what is T star T of V. T star T of W. That will just be equal to T star of, what is T of W? That is inner product of T of W will just be inner product of W with V naught times W naught. Times W rather. No, times W naught. Let me be a bit careful. So this is equal to inner product of W with V naught times T star W naught. What is T star W naught? We have just checked what T star is. T star W is W naught. So this is just going to be inner product of W naught times V naught, which is equal to W comma V naught times the length of W naught square times V naught. So if T is normal, T star TW is equal to T star W implies that the first term here is W inner product of this with itself times the length of W naught square times V naught. And how about the other one? Let me just rewrite this in this following manner. This is just going to be the inner product of W with W naught times the length of V naught square times W naught equal to 0. So this is just written in this manner. That implies that V naught and W naught are linearly dependent. Yeah, that's true because we have assumed, okay, so let's assume are non-zero vectors. Are non-zero vectors. Actually, we don't need to assume that. If V0 and if even one of them is 0, then T will be 0, T star will be 0. So hence T is a normal linear operator, and naturally if even one of them is 0, they are linearly dependent. So this is true in the case when W naught and V naught are 0 as well. So we may assume without loss of generality. So assume V naught is not the 0 vector and W naught is also not the 0 vector. The case when one of them is 0 itself is quite straightforward. And because it's not 0, this term will not be 0, this term will not be 0, and this will not be 0 for, say for example, this is not 0 for when W is equal to V naught. So yeah, so this is a linear combination, non-trivial linear combination which is equal to 0, and hence V naught and W naught are linearly dependent. Now let's prove the converse. Conversely, suppose V naught and W naught, V naught is equal to alpha times W naught, maybe C times W naught for C in the field of scalars. So here we have not assumed that this is a real or complex inner product space, so let me denote it by F. We know what is T star W and T star TW. So let's use both to see what happens when V naught is C times W naught. T star TW, let's first pick that. T star TW is inner product of W with W naught times the length of W naught square times V naught. That's what our T star TW is. But we know what V naught is. V naught is C times W naught. So this, okay, there is a slight mistake, I guess. Yeah, there is. So this is not W naught, this is V naught. Okay, so this from here will just turn out to be equal to the inner product of W with C times W naught times the length of W naught square times C times W naught. The inner product, the properties of the inner product tells us that this is C bar times inner product of W with W naught times the length of W naught square, and the C can be taken out here times the W naught here. So this is mod C square times the inner product of W naught. So let me just write it down. Times the length of W naught square times W naught. So F star let me put, so that C is not equal to 0. Again, it doesn't matter, but still. Now what is T star W? That will just turn out to be equal to, well, let me go up, let me not make mistakes. This is W naught, length of V naught square times W naught. W naught, length of V naught square times W naught. Okay, but V naught is C times W naught. So this is just directly equal to mod C square times W naught times W naught length square times W naught. But that's precisely equal to T star T W, which implies that T star is equal to T star T. So in the case when V0 and W0 are linearly dependent, then T is necessarily a normal linear operator. That completes the proof. Okay, let me stop here.